Well, my dear participants, and now I am going to talk about negative binomial distribution. Negative binomial is a very important distribution, and actually if your data is in the form of counts and it is inflated by zeros, then in that situation negative binomial fits much better than. There are examples in data analysis books. So negative binomial is a better choice than other distributions in such situations. But theoretically I would like to talk about if in a Bernoulli trial we wait for more than one success, then random variable follows negative binomial distribution. Or in R it has been implemented differently. We have to wait for the number of failures before getting R success. Number of failure before getting R success, where R is, if R is equal to 1, it becomes geometric distribution. If R is greater than 1, it becomes negative binomial distribution. So R and binom is the name in the base R, size is equal to 50 and prob is equal to 0.3. So this is the simulated data. So these are the random values which we are getting, and see mean of this data is nothing but R into 0.5 by 2. So it is mean 4.96 and variance is 7.65. And this table, frequency table, so control T underscore NB, this is the frequency table. And of course if we want a plot of this, control 1, so this is the plot of the data. This is the plot of the data. It is right skewed distribution. So this is the plot of the data. Now again, suppose we want to compute dn binom with x is equal to 3, the probability of negative binomial x is equal to 3 with size is equal to 2 and prob is equal to 0.7, then see what will be the result. It is 0.05. But if we change here the parameters, suppose your x is equal to 3, but suppose we increase the size is equal to 10 and we keep the probability is equal to this, see it increases. Similarly, if size is equal to 10 and here if we decrease this, see it is very small value, 1.60 into 10 to the power minus 8. So this way if we change the parameters, probabilities will be changed. So here control plus enter. So this is the 0.96 p binom. Prob is equal to 0.7, size q is equal to 3. 96% area is covered under before q is equal to 3. And then if we want, say for example, median of the distribution, so p is equal to 0.5, size is equal to 5 and prob is equal to 0.6. This is the median. Median is 3 and R binom psi is equal to 4, prob is equal to this thing. So this is known as R binom, and these are the 10 random observations. Suppose we assign this to say T12, and here we are having 1000 observations. Then if we get T13 is equal to table T12, so these are the T13 is the table value. So here it is right skewed distribution. From this frequency distribution, it looks like that it is right skewed distribution, and plot T12, no, it should be T13. We should have printed T13, yes. Then plot T13. See what is the distribution? The distribution is here, it is right skewed. So this way we can look into the different shape of the distribution. So this is with the binomial distribution. Now I am going to negative binomial distribution. Now I am going to talk about a very important distribution, and that is known as Poisson distribution. Poisson distribution, actually due to Poisson, it is the distribution when your output is in the form of counts. Actually, all the above distributions they talk in terms of size is equal to 4 or size. So their number of trials is fixed, and then we are getting the result. But here number of trials is not fixed. So but data is in the form of not proportions, it is in the form of counts. So Poisson distribution has only one parameter lambda called rate parameter. So to compute value of the density, the function is d Poisson x lambda, and d Poisson q, it is value of the CDF, d Poisson p, it is value of the quantile, and R Poisson n, random simulations from Poisson distribution. So here R Poisson n is equal to 100 and lambda is equal to 7. Then see what we get. Control 2 R. So these are the 100 observations from Poisson distribution with lambda is equal to 7. If we make table of R, see this distribution is somewhat right skewed, or symmetric, somewhat symmetric, it is not right skewed. So mean of the simulated data, it is 7 point, mean of Poisson random variable is nothing but the value of the lambda. So our value of lambda is 7 and simulated data mean also comes out 7. Variance of x is also 7. So it comes out variance of R 5.6, which is almost equal to 7. So this is the one distribution in which mean and variance both are same. So this is a typical distribution. Now dpoise 3, the value of the density at 3 and lambda is equal to 10. P-poise, that is the probability value of the CDF for lambda is equal to 10. So it is 0.01. And suppose we change these values, say for example P-poise lambda is equal to, if we write, say here, if we change 12, see it is 0.79. It is 0.79. Similarly, if we reduce this up to 5, this P points is 0.99. So this is the structure of, this is the role of the lambda. See, P points lambda is equal to 10. Here lambda is equal to 4. Q poise, quantile of poise with lambda is equal to quantile of poise, and it is with 0.25, lambda is equal to 14. It is this. If we simulate R1, R poise 1000 observations with lambda is equal to 2. See, lambda is 2, not large. Table. But if we plot this distribution, see what we are getting. We are getting the distribution is right skewed. So if lambda is somewhat less than 6, there is a great book on discrete distribution by Alan Agresti, which has given all these discussions, that if lambda is less than 6, the distribution is right skewed. If lambda is greater than 6, 7, 8, so as lambda increases, the distribution approaches to normal distribution. So here I am going to plot this. So here it is right skewed. It is right skewed. Now suppose if we increase lambda, Poisson tends to be normal. So here instead of 2, we are having lambda is equal to 20. Now see what is the frequency table. Control 2, T2. So here this distribution looks to be symmetric. If we get the plot, see what is the shape of the plot. See, it is very close to normal distribution. So theoretically we say if lambda approaches to infinity or lambda becomes large, this distribution can be approximated well by a normal distribution. So here now I can talk about discrete distributions and continuous distributions. So far we have been talking about discrete distributions. Now we shall talk about normal distribution. I have already told you that what is the what is the feature of discrete distribution? It talks about probabilities on discrete points, whereas continuous talks about the interval, like height of students in a class. It can be continuous variable because it always lies in some interval, whereas number of students failed, so it is in the form of count, so it follows discrete distribution. So now actually data is either discrete format or continuous format. These are the mostly two formats. So here I am going to talk about continuous distribution, and this distribution is normal distribution. See, the four main aspects of a normal distribution which are implemented in R are D norm, X, mean, SD, then P norm, Q, mean, SD, then Q norm, quantile, and then R norm, random simulation. Actually, normal distribution plays a vital role in statistical studies, and it is also known as Gaussian distribution because first it was identified by Gauss, but the fact is that it was De Moivre who identified this distribution actually in 1908, 1909. This distribution was identified by Laplace, and in 1910 it was identified by Gauss. But Gauss was very secretive in his work, so people could not decide whether it was first identified by Gauss or Laplace. But the fact is that history says that it was first identified by Laplace. But before that, it was identified by De Moivre. De Moivre was a French, and he was by creed he was Protestant. So in France he was punished for and about 2 years jail term. As soon as he got released, he left France and went to UK, England, London, and there he tried many things, but actually because of his creed he could not get any big positions, any academic positions, and but he was doing his work continuously. And see, he developed the De Moivre's central limit theorem, which is the backbone of central limit theorem. So he published his article 70 years prior to 1908 and 9, 1909 and 10. Prior to Laplace and Gauss, he published 70 years prior to them, and he identified normal distribution. And he was also introducer of the measure SD, standard deviation measure identified by him. So actually, it should be De Moivre's distribution, not Gaussian distribution. So here I would like to talk about, this was the historical background. Curve function we are going to use D norm SD from, because most of the area under normal curve it is covered on from -3 to +3. So here it is see, this is the normal distribution. This is the normal distribution. It has most of the areas are covered under -3 to +3. So If we want to compute the density of normal at 0, see what should be the value. Actually its expression is fx is equal to standard normal 1 by square root 2 pi e raised power minus x square by, its expression is like this: fx is equal to 1 by sqrt 2 into pi 2 pi into exponential of x square divided by 2. So this is the expression for standard normal distribution. So if we want to compute f0, see what will be your output. f0 is equal to f0, so 1 by square root 2 pi e raised power 0 square divided by 2. So e raised power 0 will be 1, and ultimately we are left with 1 by square root 2 pi. So that's why I have explained here that it is d binomial same as square root 2 pi, same as 1 by d binomial 0 same as 1 divided by square root 2 pi. So here d norm 0.35, and it is nothing but actually 1 divided by sqrt 2 into pi. So it is same value 0.39. So this is the value of the density at 0. Now if we want to draw a vertical line at 0 at mean of the standard normal distribution, what we have to do? We have to ebb line v is equal to 0, LWD is equal to, see, we have to run this, we have to run the whole chunk. See, this is the vertical line, this is the output of the command ebb line v is equal to 0, LWD is equal to line width is 2. So v vertical line at x is equal to 0, and this is the vertical line, and these are the lines at v is equal to minus 1.96, see ebb line. Now p norm, that is the probability, the value of the CDF at 1.96. So it is nothing but it is a well known result that value of the CDF at 1.96, that is below area under the normal curve below 1.96 is 0.975. So this is 0.975. Now if we want to plot a line, so we have to at a vertical line at 1.96, so it is 1.96. So here it is 1.96, we have added a vertical line. Similarly, at v is equal to minus 1.96, we can add v is equal to, see here the probability less than 1.96, it is p norm 1.96, it is 0.02 45, this is 0.025 actually. And if we want to add, the command is v is equal to minus 1.96, and it is this command. Here it is minus 1.96. So here area under the curve below 1.96 is 97%, below minus 1.96 it is 0.025, and area above 1.96 is 0.025. So the area between minus 1.96 to 1 plus 1.96 is 0.95, and this we can compute. Control 2, see P norm 1.96 minus P norm minus 1.96. So what we should get? We should get 0.95. So it is 0.95, the area under this. Similarly, we can compute any probability. Say for example, P norm say if we want to compute 1.96 and we want area above this, so that area is what? Area above 1.96 is what? It is area above 1.96 is 0.025. But here we have to give the additional argument lower dot tail is equal to false, because by default it computes area less than, but if we want area greater than this, so we have to write lower dot tail is equal to false, so it will compute area greater than, and it is 0.025. So this way we can get these results, area greater than. Similarly, if we want area, say for example P norm, so lower dot tail is equal to false, that means what? Area greater than minus 1.96, so it is 0.975. Similarly, so this way, suppose we want area above minus 1, so it is 84%. Above minus 1, it is 84%. And this way, suppose if we write area lower dot tail is equal to true, so here it is 84%. Lower dot tail is equal to true. And so this way we will talk further about this normal distribution in our next lecture.